All right, welcome to lecture 13 of this course on algebraic topology. Today we're going to talk about more applications of winding numbers. I'm Norman Wildberger. So today we're going to start by defining the notion of degree, and then we're going to look at a number of interesting classical theorems in planar topology that come about from applying the idea of winding number at a degree of a curve. Now, these theorems have all been historically stated in terms of the real numbers, and I don't want to upset the apple cart too much by trying to rephrase everything in terms of rational numbers, because for one thing, I don't know how to do that for all these theorems. I haven't spent a lot of time thinking about that. I think it's an excellent project, though, for someone to do. All right? An aspiring mathematician can think about how they might rephrase some of these arguments from the real number setting to the rational number setting. All right, so we're going to start off with a function from the circle to the circle. And there's our picture. Our circle is just the usual circle in the plane, x squared plus y squared equals 1. And so we're mapping that to another copy of itself. And then what we do is we're looking at the boundary curve. Let's call it alpha, going all the way around. And we look at its image under this mapping. So if, say, this point here is, let's say, call it A, and our starting point is some f of A over here. And as we go around this circle once, then the function's values will walk around on the circle in a continuous way. Our functions are always continuous unless I say so. Right? In this course, everything is continuous unless we say explicitly otherwise. Okay, so perhaps the image looks like this. It can wind back and forth, walk around. But eventually, it's going to get back to f of A, because it's a continuous map. Now, that motion, we can think of that as a curve in this plane with center, let's say, call it O prime. So this image curve, f of alpha, is a curve, well, let's say it has a winding number. And that's called the degree of f. So we say that the degree of the function f is the winding number of the curve f of alpha with respect to the center here. And in this particular example that I traced out to begin with, I think the thing went like this, and then it ended up going around, essentially went around twice. So this will be an example of the degree of f being 2. It's gone around twice, essentially in this direction. The degree is always an integer. An important remark is that if we vary the function continuously, if we change the mapping continuously, this degree is not going to change. Because it's an integer. It can't jump from 2 to 3 without dramatically changing the function. Let's define the notion of a retraction. If x and y are topological spaces, and y is contained in x, then a retraction from x to y, so let's say R, that is by definition a continuous map which satisfies that R of y equals y for y belonging to y. So for example, suppose our space X is a square, which we might say is I cross I. That's X. And Y is, say, the bottom edge. That's Y, which is just an interval. Then if we put this in the plane in the kind of usual fashion, so that this is the origin, this is our X, this is our Y, that's 1 and 1. Then a retraction from X to Y is a mapping from X to Y, which is constant, or the identity on Y itself. In other words, it leaves this part fixed and maps everything else onto Y. So in this case, a retraction would be, well, it's got a map from X to Y, so we could define it by taking the point X, Y, and sending it to X, 0. There's a point X, Y, and we'll just send it straight down to that point there, which is X, 0. Then it's clear that on the base, it leaves things fixed. Anything that's on the base is not moved. But the image of the whole thing is the Y. So this is a retraction. All right, so here's a theorem. There is no retraction from the disk D, given by x squared plus y squared less than or equal to 1, to the circle S1, given by x squared plus y squared equals 1. All right, so there's our disk. And now the circle is just the boundary. And the claim is that there's no retraction from the disk to its boundary. No continuous map that leaves the boundary fixed and moves everything else to the boundary. Of course, you can do it if you do it non-continuously. You can kind of slice it and then sort of move things over. But if you want to do it continuously, it's impossible. So, proof. Well, suppose that we did have a retraction. So suppose that R from D to S1 is a retraction. So I'm going to draw that by drawing the domain over here, this is our disk, and the image circle over here, although they're actually on the same page. So the idea is define a whole bunch of maps, let's say P sub t for t between 0 and 1. Define P of t from S1 to S1 by P sub t equals, okay, so it's going to be a composition of two things, a composition of R, but first we do scale by 1 minus t. That's a, okay, so let me draw a picture what I mean. we assume we have some map. Okay. When t is equal to 0, we're not scaling by anything. So when t is equal to 0, we just get the map from the boundary to here, p of 0. It's just r restricted to the boundary. We're not scaling at all. Okay. Now, what about when r is a quarter? When r is a quarter, I mean we're going to scale by 3/4. That just means we're going to shrink. So we're going to send the circle to the original S1 on the boundary. We're going to shrink it by 3/4, and then apply r. Okay. So that's going to, now r does something to the entire disk, so this is going to be, say, p of 3/4. And we're going to keep on defining maps until we get to p of 1/10, and then eventually p of 1. Wait, p of 1, what that does is it takes every point to 0 and sends this thing to wherever it goes. I don't know where it goes. Maybe it goes to here. There might be r of 0. So this map here would be p of 0.
P of 1.
P of 1, thank you, p of 1. We've already got p of 0. That's p of 1. So we've got this family of continuous maps from the circle to the circle, starting with p of 0, which is the identity map. The other intermediate maps are complicated. They depend on what r is. But the final map, p of 1, is a constant map. So we're going from a degree 1 map to a degree 0 map. Or in other words, this first image curve has winding number 1 because it's just the identity, while the final map, sending everything to just 1 point, has degree 0 because it doesn't go around the origin at all. So this gives a continuous family between P0, which is a degree 1 map, and P1, which is a degree 0 map from S1 to S1. But the degree is constant if we're just moving continuously. So we cannot jump from degree 1 to degree 0, make that abrupt change, if we're changing the mapping continuously. But the degree cannot change. Since P of t is continuous. And so that's impossible. So our assumption that we had a retraction is not correct. So a retraction can't exist. Our next result is a very famous theorem. It's called the Brouwer fixed point theorem. It's probably close to 100 years old. Brouwer is a famous Dutch mathematician, topologist, who also had reservations about the foundations of mathematics. And He was a very influential figure in important debates on the foundations of mathematics in the first half of the century, last century. And his theorem is really the first of many fixed point theorems that were subsequently discovered. It's a very attractive and pleasant result. It says that any continuous map, say F, from the closed disk, what we're calling D, to itself, has a fixed point. And what that means, i.e., it means there's some point such that f of x equals x. Some point that's not moved by the transformation. Proof. It's only a one-line proof. Otherwise, define a map R from the disk to the circle as follows. So suppose there's our disk, the boundary being the circle. As before. All right, so we've got a map from the disk to itself. So given any point x, there's f of x. Now suppose that x and f of x never coincide. They never coincide. Then what you can do is you just draw a ray from f of x in the direction of x, and eventually that ray will hit the circle. Well, especially if you're working over the real numbers. If you're working over the rationals, you have to be a little bit more sophisticated, but okay. So, what does that mean? That defines a map. This point now, we'll call this point R of x. So to a point in the disk, we now associate a point on the circle. And that's actually a retraction. This is a retraction. Why? Because if x was itself to start with on the circle, say x happened to be there, then no matter where it goes, when you draw the ray is going to intersect at x. So for x on the boundary, x would equal R of x. So that's the retraction property. This map would then be a retraction from the disk to the circle. But we've just proven, guess I've rubbed it off, we've just proven that such a thing does not exist. This is a retraction, but this doesn't exist. So our assumption is wrong. There must be at least one fixed point. And the standard application of that is if you have a piece of paper that's lying flat on a table, and you take that piece of paper and record where it is now, and then you do something to it and drop it back onto where it was, then there must be at least one point on the piece of paper that is directly above where it started. There's at least one point in the paper which is directly above where it started. That's the Brouwer fixed point in action. Of course, in practice, finding fixed points is not so easy. In fact, in practice, you can only find them approximately. Right? So we get back to this dichotomy between rational and irrational, but nevertheless, that's a lovely theoretical result. Fixed points are very important for economics. Economists are always looking for fixed points of situations. So this kind of topological result is very useful for them. All right, now let's talk about antipodes in preparation for a lemma of Borsuk and then a famous theorem of Borsuk-Ulam. So if we have a circle, well, our usual circle in the plane, and there's the point P, and if we reflect the point P in the origin, then this opposite point, we might call it P star. It's called the antipode of P. Okay, so here's a lemma of Borsuk. And a lot of these results were done in the 20s and 30s, almost 100 years ago. If f from the circle to the circle is a continuous map, and it has the property that it preserves antipodes in the sense that f of p star equals f of p star for any p. So if it has that property, then the degree of f is odd. The degree of f is odd, like 1 or 3 or minus 1. Proof. Okay, so here's our starting circle, S1. Let's call that point A and that point A star. And let's divide the curve around it into two pieces. So let's call this top piece alpha from here to here, and this bottom piece beta. Beta is really the antipode of alpha, right? Because as we go along here, the antipode is going along here. And now let's have a look at the image of this curve under our continuous map F. Okay. So we're going to do that in two pieces. So let's look at the image of alpha first. So f of alpha is some point, let's say there. So f of A, rather, is some point. And we're assuming that this map has the antipode property. And that means that if we know where A goes, then the antipode of A has got to go to the antipode of where A went. So if that's f of A, then this must be f of A star. So the image of the curve alpha, let me do it in red. So here's the curve alpha in red from there to there. Its image is starting here, and it's got to end there. Whatever it does, it's got to end there. So it can go around any number of times. Let's go around this time in this direction for something different. So it can wander back and forth. It can do whatever it wants. But eventually, it's got to end up back here. So let's go around 1.5 times in this case. All right, so the image of alpha was this curve that went around 1.5 times in the negative direction. Now let's have a look at the image of beta from here to here. What's going to happen to that? Well, that's going to start at f of a star, and it's going to end up there. And what does that do? Well, as alpha went in this direction, beta has always got to be antipodal to it. So as alpha was going in this direction, beta had to head in this direction. So if alpha went around 1.5 times this way, then beta's got to go around 1.5 times in this direction. So f of beta is antipodal to f of alpha. So its turn is well, it's going to be the same, n plus a half. The same n. It's going around the same number of times, plus a half. So if we put these together, so the total turn is tau total. It's n plus a half plus n plus a half. That's 2n plus 1. That's odd. Next time we will talk about the Boursac-Ulam theorem, which is a consequence of this lemma, and the ham sandwich theorem. So I'll see you then.